Hello and welcome to a new chapter of mathematics which is based on the application of integrals. Today we shall be finding the areas of bounded region, and later we are going to evaluate some numerical problems that would be based on finding the area of the bounded regions using the integrals. So starting with discussing the area of a bounded region. Now, the first step in finding the area of bounded region is to identify the region whose area is to be computed. And for this, we need to draw the graph or the rough sketch of the various curves which enclose the region. Now, we have the first theorem which states that let fx be a continuous function defined on interval ab, then the area bounded by the curve y equal to fx, the x-axis and the ordinates where x is equal to a and x is equal to b is given by integral of fx with respect to x with the limits a to b, or we can replace fx by y and we have the integral as integral of y with respect to x from a to b. And if the curve y equal to fx lies below x-axis, then the area bounded by the curve y equal to fx, the x-axis and the ordinates x equal to a and x equal to b is negative, and so the area is given by modulus of integral of y with respect to x from a to b. Similarly, if the curve y equal to fx lies above x-axis and the area bounded by the curve x equal to fy, the y-axis and the abscissa y equal to c and y equal to d is given as integral of fy with respect to y from c to d, or integral of x with respect to y from c to d, where we have replaced fy by x. Next, we are going to find the algorithm which can be used to find the area of a bounded region. So, in order to find the area of bounded regions, we use the following algorithm, in which the first step is to make a rough sketch showing the area to be found. The next step is to slice the area into horizontal or vertical strips as required in the given problem. The third step is to consider a representative strip and the corresponding approximating rectangle. The fourth step is to find the area of the approximating rectangle. If the representative strip is parallel to the y-axis, then its width is taken as delta x, and if it is parallel to x-axis, then its width is taken as delta y. Next step is to find the limits within which the approximating rectangle can move. Now let's consider a curve which is fx and is of this form. That means fx is continuous in nature, and in order to find the approximating rectangle of this curve, first we need to find the approximating rectangle of the area y delta x that can move between x equal to a and x equal to b. Therefore, the area bounded by the curve y equal to fx, y equal to 0, x equal to a, x equal to b is given by integral of y with respect to x with limits a to b. Next, we are going to consider a problem in which we have to find the area bounded by the parabola y square equal to 4ax and its latest rectum. Now, a rough sketch of the parabola y equal to 4ax can be drawn as shown. Now here, let S with coordinates a and 0 be the focus and L, S, L dash be the directrix of the parabola y equal to 4ax. The required area is L, O, L dash L. Since the curve is symmetrical about x-axis. So the required area is equal to twice of area of LOSL. Here we are going to slice the area LOSL into vertical strips for approximating rectangle as shown in this figure. Now the length of this approximating rectangle is, let's say, y, and its width is delta x. Therefore, the area of this approximating rectangle is equal to y delta x. This implies that area is equal to root of 4a x into delta x. Since y given here can be evaluated by this parabolic equation, which is y square equal to 4a x. Now since the approximating rectangle can move from 0 to a, therefore required area is equal to twice of area of LOSL. This is equal to twice of integral with limits 0 to a root of 4ax delta x is written as dx. This is further simplified as 4 into root of a into integral with limits 0 to a root of x with respect to x. This is equal to 4 root a, and this integral is evaluated and we have the value of this integral as x to power 3 by 2 divided by 3 by 2, and the limits of this is equal to 0 to a. Now simplifying this, we have the value as 4 into root a into 2 by 3 into a to power 2 by 3 minus 0, which is equal to 8 by 3 a square. Thus we have found that the area bounded by the parabola whose equation is given as y equal to 4ax and its latest rectum is equal to 8 by 3 a square units, which is found by the use of the definite integrals as was discussed in this lecture. With this we conclude the first lecture on applications of integrals, which was based on finding the area bounded by the given curves.